This looks like a hogger up here.
I saw Donna.
This hogger?
Yeah.
Yeah.
What if someone went up behind you and just cut the
Okay, we've got a handout. Warm up on front. As I mentioned this morning, once we get through today, we should be able to do 1 through 5. And number 6 is kind of below that, I think. Document and okay. So we're in chapter 16 of the Fine textbook. Of course, any organic textbook is going to have a chapter on NMR and cover the same topics, essentially. So, let's work towards being able to work the front, but there's much more to it. In the workbook, in the workbook, there are comprehensive spec problems. There was one on the pre-course worksheet. That's the type of problem you'll see on the test. Okay. So I think I showed this when we did mass spec. Here are 2 IRs. Up there you got 2 alcohols. Which IR goes with which compound?
No.
That first one goes to the bottom.
How do you know?
That's just my guess.
Yes. Both IRs show a broad OH peak. Both IRs show peaks just below 3,000 sp3c8. They do have different fingerprints, but that does you no good unless you can match it up to something. If you find someone's fingerprint on the doorknob, I can tell you who it is. You've got to match it up to somebody's fingerprint. I don't know which is which. IR has limitations. That's what we said when we introduced mass spec. But if we did NMR on those 2 compounds, telling them apart would be so easy. NMR tells you more about the carbon and hydrogen backbone. Okay? We flip over, we see the NMR of each compound. Now when we say NMR, we typically have to clarify. The most common is proton NMR. Proton meaning hydrogen. And the one isotope with just 1 proton, no neutron. All this is a proton. That's why we call it proton. So this is H NMR. The other type of NMR that we will cover is carbon NMR. So first thing is make sure you know which type of NMR we're talking about. H NMR has a baseline in ppm that goes from about 0 to 10 or 12. Carbon NMR goes from about 0 to 200. Okay? So these are proton NMRs. The main thing that I want to show you first, and one of the first things we'll talk about once we get really into this, is how many signals do you expect for this alcohol? What do you want to call that? 1 propanol? 1 propanol. How many signals? Another way to ask is, how many different types of hydrogens in 1 propanol? There are 4 types of hydrogens. These 3 on the end. Okay, there's a CH3 on the end. First off, the CH3, each of those 3 are equivalent due to free rotation. I labeled those 3 as the A type. That's 1 type. Okay, there's 2 on this carbon over here that's labeled B. Are those 2 the same as the 3 on the end?
Yeah.
No. Those are closer to the hydroxy group. Basically, the only way they're going to be the same is if we have symmetry in the molecule. This molecule doesn't have any symmetry. Not that would make A different, A the same as B. B is different. How about the 2 H's on carbon C? Are those different than B? Yeah, those 2 H's are closer to the hydroxy group, even closer. What makes them different is really like electronegative effects. The two H's on C are experiencing more of the pull of the oxygen than the two on B. So that's the third type. Where's the fourth type? Obviously, it's the one that's on the oxygen. That's the fourth type. 4 unique types of hydrogen in this molecule. You will thus get 4 signals in the hydrogen NMR. That's the first thing we want to get across. Here are your 4 signals. Boom, 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 boom. Now, the next thing we want to get across is, well, this signal, that's one signal, but it has 3 lines. We're going to eventually call these like a triplet. And that's my T. Okay, it's supposed to be sort of curved at the bottom, so it won't look like a plus. It's a T for triplet. This is a singlet, it's 1 line. This is multiplet because it's many lines. And this is a 1, 2, 3, what is that? Just like this, that's a triplet, T. So our signals will have different, what's called multiplicities, or different line splitting. But that is 1, 2, 4 signals. Because we have 4 different types of hydrogen. Let's move down here. This is 2-propanol, also known as isopropanol. It's an isomer of the other one. How many different types of hydrogen? Obviously, I've already got them lettered for you. CH3 over here. What about that CH3 over there? Is that different? No, because of symmetry, these are the same. This CH3 is a bond away from the CH that's connected to the O. This CH3 is a bond away from the CH that's connected to the O. Each of these 3 are the same. That means that's 1 type. How many H's of that 1 type? 6. 3 and 3 make 6. All 6 are the same. I call them the A type. Then we got an H that's on a carbon over here. Well, obviously, that H is not the same as these 3. Because it's on a carbon that's close to oxygen. So it's unique. How many of those types of H's? Only 1 of those. And then what's the third type? Obviously, it's the one on the oxygen. Everybody agree that you see 3 types of H's in this molecule? We do have symmetry here, which makes the 2 methyls equivalent. 3 signals, 3 different types of H's, only 3 signals. 1, 2, 3. This is a multiplet, that's a singlet, that's a doublet. The H's here is the number of H's for the signal. Remember 6H? Well, A is going to be a doublet. We'll learn why a little bit later. So once you become knowledgeable of this stuff, what you do is you look at the 2 alcohols and say, hey, I expect 4 signals for this one, 3 signals for this one. Boom. If you were asked which one is this, you'd say, hey, oh, it's that one, because I expect 3 signals. That's how many I got. Okay. Once we get more into it, you can come back and look at why it's a multiplet. We'll learn about that. We'll also learn why this signal is more to the left. By the way, we don't usually call it more to the left. Usually we say more downfield. So we're going to have terminology we can use to talk about our spectrum. We will do this introduction in layers. This is sort of a little bit of intro. I'll move on to more intro and then we'll address other things. Okay. On the flip side is really something you can come back to. This is melatonin. Isn't that like the sleep hormone? Okay. Here's the NMR of melatonin. You could go through here and say, how many signals do I expect? How many different types of hydrogen? And you can get the signals. Okay? That's H&MR, melatonin. H&MR, right? Because we're on 0 to 10 ppm. It's also an IR up there. Okay. That's just kind of for reference. You can come back and look at that once we learn more about NMR. Okay, let's do some more overview. Especially, let's look at this terminology that's in this box down here. First, the spectrum. As I mentioned, ppm is plotted here. NMR is a type of spectroscopy. We are using light, just like in IR, just like in UV vis. But we don't plot frequency here, or even wavelength. In IR, what do you plot? What's the baseline? Absorbance? No, baseline is, I'm talking about the x-axis. Absorbance is more the y-axis.
That's wavelength, or wave number.
Wave number, which is a reciprocal wavelength. Basically, you're applying wavelength in IR. What do you plot in UV vis? I have a peak at like 400 nanometers. Using nanometers. Nanometers is what? Yeah, that's a direct wavelength plot. In NMR, you don't plot wavelength. You also don't plot frequency. But you are using light. What you plot is ppm. Now, obviously, that's parts per million. So we'll have to eventually define what it really refers to and why it's used, etc. Not going to do that quite yet. Peak position is very important. For example, this peak we say occurs at about 7.2 ppm. You could also say this occurs at 7.2, a delta value of 7.2, because the ppm numbers are also known as delta values. Of course, this is a large ppm. It would also be a large delta value. It's just different terminology. Okay. There's an NMR of that compound there. You actually expect 5 signals, but you only get 3. Let's don't talk about that. When you do NMR, typically you have to include an internal standard. Most common internal standard is this guy here, known as TMS. That's silicon, and it's known as a silane. What do you think TMS stands for? How many methyls on this silane chain? Yes. Tetramethylsilane is the most common standard. You set that at 0 ppm. By the way, how many different H's in TMS? Only one type, because all methyls are equivalent. So it only gives one signal. Turns out that it's actually a singlet, and there it is right there. One signal, that's the TMS signal. You set it at 0. Why do you have to use an internal standard? In IR, you don't have to do this. In IR, the IR is very uniformly generated. 4,000 to like 400 reciprocal centimeters.
You have calibration for each test you run?
In IR? Or?
I don't know for this.
Yeah, but why? The reason is, well, we haven't pointed out yet that you got to use a magnet. That's the M of NMR. But your magnetic field strength can vary day to day. And so your peak position varies day to day. It'd be very confusing if one day the peak was at 7.2 and then next week you're running it at 7.4 because the magnet changed its strength. To account for that, we include a standard. We set it at 0 and then we say this peak is always 7.2 downfield from TMS. Now, if the magnet drifts, maybe this goes here. Well, that's okay. We can calibrate it by putting this back where? To 0. And we can get back our... constant result. Okay, the magnet drifting is analogous to, you know, old radios with the little dial you tune in your radio station? It's fuzzy. You guys don't know this. Some of you may. Right? You get it set just right. You get the antenna pulled out. Oh, it's coming in good. You come back the next day and the sound is no longer coming in good. Nobody moved the dial, but what happened? The signal coming from the tower wherever got changed. What do you have to do? You have to tweak it again.
Which uses the internal magnetic field to do the tweak magnets.
You probably know more than me. But it's kind of like that. Well, this is dependent on a magnetic field, which we haven't even discussed yet. Okay, terminology here. We're going to say these are protons in electron poor environments. It's electron rich or dense, that way. These H's that are giving this signal are in a more electron poor environment, because they're more this way. We also say the H's that give the signal that's more this way are de-shielded, where H's that give signals over here are said to be shielded. We're going to explain this right now, just sort of pointing it out. This is called downfield, that's called upfield. Students often get this wrong, because down sounds like a lower number. Actually not. Downfield is actually higher PTM. This is the most downfield signal up here. That's the most upfield signal. Or if you discount that because it's really just internal standard, then you say that's the most upfield signal. Terminology. In terms of frequency, which we're not plotting, and we will very rarely refer to actually. But this is actually the high frequency end, that's the low frequency end. I think that's probably the least important of the up there. Why is this called upfield? Well, in the olden days, we had the original experiment. To get this peak to show up, you used to have to turn the magnet up. And so you'd say it's more upfield. It's referring to the magnetic field strength. But today, you don't change the magnetic field strength. You hold that constant. That's just kind of that's a side point, but that's where that terminology comes from. Okay, let me say this, guys. NMR, there's lots here. That's not necessarily difficult. But it is many components to it. Because there's many components, that's why it's so powerful and sort of the most important of the organic techniques. We will use this terminology, and eventually you won't even have to think about what these terms mean. You'll just know. Okay, quick word about sample prep. A few milligrams. Important thing is you have to dissolve it in a solvent. When you do IR, you don't dissolve it. You just put the compound on the IR and press the hammer on it or something. NMR, you have to dissolve it. You want to dissolve it in a solvent that doesn't give NMR peaks, or many NMR peaks. When the original was carbon tetrachloride. There's no H, so it's not going to give a signal in the H-NMR. You don't want your solvent to give a signal because it would be a huge signal compared to your solute. The problem with carbon tetrachloride is it's a lousy solvent because it's non-polar. It's also fairly toxic. A better solvent is if you replace one of these with an H. I know the name of that one. IUPAC would be like trichloromethane. Nobody calls it that. This was actually used as an anesthetic back in World War II. Queen Victoria inhaled it when she gave birth, and it became a big thing. Chloroform. Yes. Okay. Well, it's better solvent because it's polar. Okay. It's got a dipole, permanent dipole. It's tetrahedral, right? Better solvent, but now we got an H. And that would give a huge signal in the H NMR. And it turns out that's just not good. So chemists wanting to always develop something new, a tricky way to do here is replace the H with a D. We've used D a good bit in class, right? Just an isotope of hydrogen. D does not give a NMR signal in the proton NMR. So now we're good to go. It's still polar, but it doesn't give a signal. So what you typically use is deuterated solvents. You can buy these. This is called CdCl3 or like deuterochloroform. I don't like the solvent still. My favorite solvent is this one, which is, if these were methyls, anybody know this one? Dimethyl sulfoxide. Dimethyl sulfoxide, also known as DMSO. May have been on the solvent list I gave you in organic 1, here in week 1. 6 H's, that'd be a huge signal, but we can replace them all with D's. Change these to D's, you get DMSO D6. And usually that D is written lowercase. I'm not quite sure, but it always is. Not quite sure why, because usually when you write an element, you write capital, right? So that's more polar. Because it's got this very polarizing pi bond. That's a good solvent. Basically, once you dissolve it, you put it in an NMR tube. An NMR tube is about the size of a straw. Here's an example. You put about an inch and a half or so. Just put a little plastic cap on it. And now it's good to go through your NMR. Run your sample, run your experiment. Okay. Anything on that page before we turn on?
We add the TMS to that mixture.
Oh yeah, I think it says that at the end. Yeah. Typically, once you dissolve it, you can then add like a very small drop of TMS here. Sometimes your solvents come with TMS already in. Okay. That was overview. Now what we want to get into is really what's going on with NMR and how do you get signals? Why do you need the magnet? Etc. What is this downfield versus upfield thing? Can you do NMR on every type of element or what? These are some of the questions. Okay, first off, NMR stands for nuclear magnetic resonance because we're dealing with the nucleus of the atom. In IR, what are you dealing with? Bonds, not the nuclei, the bonds. And their vibration. NMR, you're dealing with the nucleus. Okay, we're dealing with the magnetic properties of that, so nuclear magnetic. Resonance. Resonance is a term when you get that absorbance. And when you see a peak in NMR, it's absorbing light. We'll have to figure out why and explain why. So that's what NMR. NMR, very analogous to what at the hospital? MRI. Okay. Tell you a little bit more about that. Okay. The NMR phenomenon. Why do we get a spin? What's this magnetic property? Okay. Let's start with this premise. All nuclei that have a net spin, that is a spin quantum number of greater than 0. Spin quantum number is also known as capital I. So if it has an I greater than 0, it will have a net spin. Any nucleus that has a net spin will have a magnetic moment associated with it. Why? What's the charge of a nucleus? Positive. And if a positive charge is spinning, what does it create? A magnetic field. This is showing it right here. This is nucleus, positive charge, spinning, it creates a magnetic field. It's going to have a direction for that field. Is that known as a vector or something? A vector
Right
prop-
hand going across, vector cross product.
There's directionality, so it's called a vector. Okay. Now, if it doesn't have a spin, it's not going to create a magnetic field, and you can't do NMR. You have to have the nucleus has to have a magnetic field. All right, so that's the first premise. First off, how do we know which ones have a spin greater than 0? Do we have to memorize them all?
I hope not.
No. We're going to tell you how to do it, and then you can answer any of them up there. Any nucleus with an odd number of protons or neutrons will have a net spin. That is an I greater than 0. Another way to say this is any nucleus with an odd atomic number or mass number will have a net spin and thus be NMR active. Essentially, we're looking for an odd number of protons or neutrons. If it has that, it will be NMR active. What about simple proton? How many protons does it have? This isotope of hydrogen, how many protons? 1. What's the atomic number? 1. That's the number of protons. Okay? Now, that can vary, different isotopes. But if I'm saying the isotope is 1, how many neutrons does that have? 0. So all it is what? 1 proton. That's why we call it a proton. Does it have an odd number of protons?
Yes.
Yes. That's going to be NMR. That's it. You read this here. That's all it takes. One of them being odd. Okay, deuterium. That's where you really don't need to write this 1, because any H is going to have a subscript 1, right? That's the atomic number. What about the isotope with a 2 here? Mass number of 2. How many protons? 1. Do we even have to ask how many neutrons? No. If it has an odd number of protons, NMR active. Any nucleus with an odd number of protons will have a spin greater than 0 and thus be NMR active. See, deuterium is NMR active.
Just not in the range of a proton NMR.
Thank you. Just not in the range of this guy. Because when we IR, we scan a big range. In NMR, we actually scan relatively fairly small ranges. So maybe this is proton, and deuterium may be over here. So when we plot this spectrum, that signal's not in this spectrum. Okay. Carbon-12 is the most abundant isotope of carbon. Is it NMR active?
No.
Well, you can read that. But why is it not? How many protons?
6.
That's not I. How many neutrons? 6. That's not I. Game over. Sorry, it does not have a net spin. I equals 0 for this guy. No net spin, thus not NMR active. Now we haven't said why it has to have a net spin. We're just saying that it does for now. We'll explain more later. But what about carbon-13? How many protons?
6.
All carbons have 6. How many neutrons?
7.
Ah, that's odd. Odd number of neutrons. So what's does this have a net spin?
Yes.
NMR active. See, all these are NMR active. Fluorine-19. How many protons? 9. NMR active. What about oxygen-16, which is the most common? How many protons? 8 protons. And how many neutrons?
8.
Sorry, both are even. Game over. You cannot do NMR on O16, but you can on O17, because how many neutrons does it have? 9. Okay? In the end, you can do NMR on just about anything on the periodic table, as long as you're doing the right isotopes. What about about boron 10? Can you do NMR on boron 10? Yes. How many protons? Can you do NMR on any boron isotope?
Yes.
Yeah, because any boron isotope is going to have 5 protons. What about iron 56? Iron 56. Can you do NMR on this isotope? How many protons? 26. Write that here. That's the atomic number. How many neutrons? 30. Either one is odd. Can't do NMR. What about iron? What would be the next closest? Like maybe 55? Can you do iron 55?
Yes.
26 protons, how many neutrons? 29 neutrons, that's odd. It'll have a net spin. What is the net spin? I don't know, you have to look it up in some table, but I guarantee it's not going to be 0. Now, sometimes, it depends on what that net spin is. It may be easy to do the NMR, or it may be pretty difficult. But theoretically, you can do NMR on iron 55, where you absolutely cannot on iron 56. O17 is often done with oxygen compounds, with oxygen nuclei. But this is sort of a very minor isotope. So you don't have a lot of sensitivity when you're doing this, because it's not that abundant. Whenever we do carbon NMR, we'll be doing the NMR on C13. C12 is not NMR active. Next, let's look at the absorption process and how do we get a peak? What's going on? What's that? Sounds like that. I don't know. I remember that show Lost where that thing would go ding, ding, ding. Right? Mash the button or something. Type in the code. My son is rewatching Lost. I didn't realize how many flashbacks they have on this show. Half the time they're not on the island. Okay, why do we get a signal? How? Okay. Now let's say we're doing proton NMR. Let's say I've dissolved a compound that has lots of different protons, like we looked at the very beginning. Okay? And it's got maybe 4 types of protons. Okay, we did that. Thus it has hydrogen nuclei. Okay? Maybe in each molecule there's 12 hydrogen nuclei. And each of those nuclei has a magnetic field. Causes it spinning and creates a magnetic field. But all those fields, all those 12 fields for the 12 H's are sort of random. Random in terms of their direction. And that's what I illustrate here. Nuclei with random magnetic field directions. Okay? But it turns out if you put that sample into a magnet, like a really big magnet, and that's denoted by this field direction here, and I have it just going up, something will happen to these. They will no longer be random. Instead, they will line up in 2 different ways. They will line up either with the external field. Okay? Now I just showed 6 here, but it could be however many H's are in your molecule, or however many carbons are in your molecule in carbon anymore. That's called the alpha state. It's lower in energy because it's lined up with it. But you'll also have some of those nuclei line up against the external field.
Will it always be half and half?
Good question. It's very close to half and half. You might think that this is not desirable. But this is actually very close, and the distribution is based on like a Boltzmann distribution. And if you do it, I think I've seen, like for every million you have, for every million you have here, you got like 1,000,007 here. So there's only 7 more here for every million.
So what's that?
Do it?
Do we like know why?
Well, because this is lower in energy,
And that's just favorable?
and it's more favorable. But only a wee bit,
Yeah.
okay? Not highly favorable. What the external magnet does, it gives you 2 states. 2 discrete energy states now, where over there you didn't have any discrete energy states. Now, we can put energy in, right here I'll show you that. We can add light energy, h nu, okay, into the system, and the nuclei will actually absorb that light, and they will take on the energy and become a higher energy level. And what do we call the higher energy level? They become the beta state. They will actually undergo a spin flip. That's analogous to go back to IR. Molecules minding this business, vibrating. Okay? Somebody throw me some IR.
I did.
I didn't catch it. What did I do? I absorbed it and went to a higher energy state. We call that a higher vibrational state. Okay? Now, how did I absorb it? It's very physics related. Okay? How does this absorb it? That's a little bit beyond us. Okay? But it will, and when it does, those nuclei do a spin flip. Okay? But then, so now we can plot the absorbance. By the way, you can absorb. The other way is the ones in the beta state can relax and give the energy back off and relax back down to the alpha state. Now, the only reason I point that out is because actually what we measure is we don't actually measure absorption, we actually measure relaxation. But it's the same thing essentially. But we will use the term relax later on. That's the energy being given back out. Because remember, we never talked about it, but the bond may go up here. Does it stay up there forever? No, it falls back down to, okay, we didn't talk about how, but now this gap in energy, it's a very small gap. It doesn't take much energy and everything's quantized. If you throw UV at that, it won't do anything with it. If you throw IR at it, it won't do anything with it. What type of light do we have to throw at it to get it to absorb?
High energy.
Radio frequency, which is the weakest on your electromagnetic spectrum. Very weak energy that will do that. Now, how do we get different signals? Because right now I haven't said, if the difference in all the states in the molecule is the same, and the delta E is the same, you'll just get one absorbance. So how do we get 3 or 4 absorbances? This delta E varies for each type of proton. And thus you get 4 different delta E's, and thus you need 4 different radio frequency wavelengths. 4 different absorbers. Why does the delta E vary for each type of proton? Let's try to explain that on the next page. Okay, stuff up here, let's kind of go straight to this diagram. This illustrates a very important point. The gap in between your 2 states, your delta E, first off, is dependent on the applied or so-called external field strength. And as this increases coming across the x-axis, what happens to the gap in your alpha and beta state? Well, if we got, say this is 0 and this is 100. By the way, I mean, how do you measure field strength, magnetic? What type of?
Teslas.
Tesla or Gauss, is that right?
Yeah, Gauss is a.
10,000? 10,000 Gauss is a Tesla, is that right? I can't remember. Okay, well, let's say it's just arbitrarily, this is a higher field. Here, what's the gap in your alpha and beta? That much. This is integer. What if we increase the field strength to way over here? What happens to the gap?
It's bigger.
It's bigger. What this is illustrating is the gap is based on the field strength. Okay? By the way, I did bring this. Make your sample. You go to the NMR. I don't have a picture of an NMR, but it has a magnet in there. Usually a superconducting magnet. All this is kind of covered with plastic. You have to open it up to see it. You'll see this in like physics. Plug this into a battery, is that right? And create as the current runs through here, it creates a magnetic field. Then what do? Then you put your sample in here. There's a way to keep it there. And once you put it in, what do you establish? The two different states, the alpha and okay. Here they're random. Put it in here, boom, they line up. Either with or with. What happens to a compass if you came from outer space or wherever and you had a compass in it? As you came to Earth, what would that compass do?
Point north.
Why does it point north?
It's because it's magnetic south.
Because it lines up with the magnetic field of the Earth. Okay? Isn't the compass a little magnet itself? That's the same idea. The big Earth field makes the compass line up. Okay. Now, this can vary because you can have different magnet sizes. Smaller magnets, bigger magnets. That's not really applicable to us, but that should make sense. Still need to get at why do we get different signals? Because let's say this has this magnetic field strength. We put it in, all the hydrogens will experience this, so the gap for all the hydrogens will be what? That. We still haven't said why the gap, how does the gap vary for each hydrogen? It looks like it should all be like that. The reason they vary is because they don't all feel the same applied field strength. What they actually feel is called B effective. This comes from that, but this is modified by B local. And this is the thing that varies. What is B local? It's a local magnetic field. Okay? This is the external one, like this thing here. B local is another magnetic field that is produced by the electrons nearby the protons. They produce their own magnetic field. Now, I often struggle to explain this very succinctly, and I found a diagram here. I didn't use it yesterday, but we got this on camera. Maybe this will explain it. Here's the external field called B naught. Here's a nucleus. What's around the nucleus? Electrons. This will induce circulation of the electrons. Why? Hopefully you might get it out of physics, and some of you may. Okay. Basically, this induces the circulation, which then leads to electrons have a charge, And if they're rotating, what do they produce?
Magnetic field.
Produce their own. Well, it turns out that one coming from the electrons, which we're going to call BE, can't really see it, B electron, it opposes this one. It has to based on somebody's law.
Any questions?
In physics, what?
Lenz's law.
Lenz's law. Very good.
Is that right? Or,
Lenz's law?
okay, yeah. I thought you were just joking.
No. Doesn't Lenz's law say an induced magnetic field will
Yeah.
oppose the one that originally induced it?
Yeah.
Something like that?
You just smiled and threw me off. Like,
Well, the reason I smile is because I act like I knew it forever. I've only recently kind of tried to learn more of this physics. The reason why is because I know you guys are seeing it in your physics classes. I'm trying to relate more to the physics, okay? But it does, I always just knew it opposes it. But, so now I can say Lenz's law. Okay, but it turns out is, this is not going to vary. Because this thing doesn't vary that it's in. But this does. Why does this vary? This varies due to, I know you don't have this, and I don't know how to spell varies. It varies due to electron density. It varies due to electron density. Now tell me this. Do each type of hydrogen have a different electron density? I mean, sure. Look at here. Look at something that writes. 2 H's here, 3 H's here. Are these experiencing the same electron density as these?
no.
No. These, which has less electron density? Right or left?
The middle one.
Has less because it's closer to that greedy chlorine. Okay? We expect two signals. Why? Because they have different electron density. That's going to make this vary. Because that varies and that adjusts this, it's going to adjust it two different ways. Or two different amounts. Basically, we can go back to, that's constant. This varies based on electron density, essentially. Because that varies, what the nucleus actually senses varies. And because it varies, you end up with different places on that magnetic field, and thus you get different signals, because you have different gaps. Now, most of this is trying to be explained here. I'm not going to read it to you. I do want to explain the bottom, but before we do that, any questions here? Did we get to how you get a signal and why do you get different signals? Are we good?
Yes.
Questions? Of course, this has got to kind of sink in. You got to think about it. Any questions at this point? Asma, question? Okay. Let's relate this back to more of a spectrum. Oh, let's use some terminology over here before we go on. This field here, is it opposing this field or adding to it?
Opposing.
Opposing. So do you want to call this effect a shielding effect or de-shielding? Is it shielding the nucleus from this? Yeah, it's shielding it. Because the more you have of this, the less of this it feels. This is a shielding effect. And thus, the less you have of this, more is more of a de-shielding. See, electrons are known to shield because the electrons create a field that opposes this. And I usually give the analogy of shielding to sunscreen. This is the sun. The electrons act like sunscreen and oppose the sun. Opposing the sun makes you feel less sun, right? And so we would say the sunscreen is like a shielding effect. Shielding you from the sun, this is shielding you from feeling so much magnet because it's going the other way. It's opposing. That's why up here that's a negative. Because it's the B local opposes that and makes the B effective lower. Okay, let's go down here and see if we can equate this to an NMR. Now we can have two different energy gaps because these H's fill a B effective of this degree, these H's fill one here. Of course, the more it fills, the wider the gap. Try not to read anything. Let me ask you here. Left or right? Which signal is said to be more shielded?
Left.
Here left. Anybody say right? Is shielding going to make you feel more magnet or less?
Less.
Make you feel less. And if you feel less, is there going to be a bigger gap or smaller? Smaller. See, this is a shielded. Now, the NMR is shielded more to the right or left? You have to look back at that terminology. Yes, to the right. This gives a signal more to the right. Okay? This is my shielding effect. Or this is a consequence of shielding. This is not as much shielding, so we call it de-shielded. And the de-shielded signal is more to the left. That would go with that one. Just in terms of relative. I'm not worried about actual ppm.
Dr. Stevens, so if that induced magnetic field by the electrons is what causes more shielding to happen, and since it counteracts the
Counteracts this?
yeah, exactly. Does that mean de-shielding would be if the induced electric or magnetic field matches the one that's up below?
Now, de-shielding is just sort of the opposite of shielding. It's never going to add to it.
Okay.
It'll just be less. And so we call this a shielding. We say that's de-shielded only relative to it's not as much shielding as this. Okay? This is relative comparison. We'll use the terminology more and see. Okay. That's the overview for the intro. Okay. So about theory. What it now is, well, how do you use this stuff? How do you interpret? Four main things we're going to look at. One thing we've already done at the very beginning. We're going to look at number of signals expected, peak position, why some signals are more upfield versus downfield. We're going to integrate signals. That'll tell us how many nuclei we're dealing with. And then we'll look at coupling or multiplicity. That's the signals being like singlets, doublets, triplets, quartets. Why are they like that? First thing, number of signals. Most of these are already labeled for you. Let's just make sure we agree with the labeling. Then we'll do some on our own. What is this? 1-bromopropane? How many different types of hydrogen? Everybody agree it's 3 types? Which type, A, B, or C, is experiencing more de-shielding? De-shielding. So what we got here? Bromine's going to pool. So is C the most electron rich or most electron poor? Electron poor. Is electron poor going to give you more shielding, or is that going to, we might call it de-shielding? Electron shield. If you got less electrons, that ain't shielding. That's more towards de-shielding, the opposite. So we say it's de-shielded. So C, you would expect to be more upfield or downfield? Yes, downfield. Okay? Just trying to review and get you. Okay? Everybody agree this is only 2 signals. Because the symmetry, these methyls are the same. They're both bonded to a CH, it's bonded to a bromine. Symmetry there. Everybody agree this is 3. Are these methyls the same? No, one's bonded to oxygen, one's not. Which methyl, A or B, would be more deshielded?
B.
B. Oxygen and deshield. Greedy atoms deshield the neighbor. They're pulling electrons away. Everybody agree it's only one signal because both methyls here are the same? Methyl terbutyl ether, how many signals? Obviously 2. All these methyls are the same. That methyl's different. What about integration? That is number of H's per signal. How many H's for A? 9. How many H's for B?
3.
Okay. That's your integration. Or we can boil this down to 3 to 1. NMR you can integrate or really quantify like that, which you can't do in IR. IR peaks don't tell you how many H's there are. NMR does. We'll get to that. 2 signals, yeah, makes sense. How about this guy? Everybody agree these methyls are the same? These H's are the same? 2 signals. How about over here? Everybody agree these H's are not the same?
Bromine.
Because they're not the same. Are they not the same? David, why are they not the same? Why does a double bond make them not the same? Because one is trans to the bromine and one is cis. Okay? Now, in terms of bond distance, they may be, single bond to one single, single bond to one single. But through space is also important. And through space, this one's just closer to the bromine than that one. Question?
So if in the first example, or second example on that line, if one of the hydrogens on the other side was like a methyl, would it be the same as A?
If that's a methyl, these two are no longer the same.
Okay.
Because one is cis to the methyl, the other is trans to the methyl.
So all 3 of them would be different? Or?
Yeah.
Okay.
If that was a methyl, they're all 3 methyls are different. Just because they're on the same carbon doesn't make them the same. The only thing that made that CH2 the same is, what did I say? Free rotation. Double bond ruins your free rotation. It's fixed. Right? Like right here, all 3 H's are different. Shelby, A, B, C. Just because these are on the same carbon doesn't make them the same.
So
How about-
this,
Yeah.
the cis-trans thing doesn't really apply to the second example because they were both technically both close to a methyl.
Here?
Yeah.
Well, this methyl is cis to an H and trans to an H. This methyl is cis to an H, trans to an H. It's the same.
Symmetry wouldn't happen.
Well, you have, it's ultimately you have symmetry. Benzene, how many signals? 1. Benzene just gets 1 signal. What about nitrobenzene? 3. These two are the same. You got symmetry here. And it can go right through that group. These two are the same, those two are the same, this one's different. These two are both next to a carbon with a nitro. These two are both next to carbon, CH is next to nitro. This H is unique. 3 signals. Let's do some on our own. How about butane? How many signals?
2.
Somebody?
2.
A, B. What is this over here?
A.
That's also A. I'm gonna call A prime, and this is B prime. These two methyls are the same. These two CH2s are the same.
So there doesn't have to be an electronegative atom involved.
Why do you ask if it has to be on negative atom?
Yeah, because before we were talking about ones with O's and stuff.
Well, that's referring to shielding, de-shielding. We're not saying where the signals will be. Hey, there's no de-shielding here, really. There's nothing de-shielding. We'll talk about peak position in a little bit. Right now, this number of signals is 2 signals. How many signals for this? 3. Somebody got it? 5? 5? 5. A, B, C, D, E. Is that methyl the same as that methyl? No, this methyl is closer to the C nitrogen. There's no symmetry there.
Could you argue that there might be 6 here?
Which one are you saying?
The E would have, instead of E would be an E and an F.
Which one?
The nitrogen, with the 2 hydrogens there, would be an E
Uh,
and an F.
You're actually onto something, but
There's no symmetry there that I could see.
you think these two are different?
I would think so.
That is tetrahedral. Well, not these two.
Okay.
And I reckon I'm lying a little bit about 5, because I don't want to get here. I'm not sure these two on B are the same. I could think they're not. This happens to be a bad example because it gets into something that I don't want to get into.
B and D aren't the same because, or why aren't B the same?
Well, B is bonded to an extra methyl, D is not.
So does it mean that they're both like one away from the,
Well, yeah, they are, but B has a methyl bond to it, where D doesn't. And that's enough to make the difference.
So this, we wouldn't be able to tell whether the B's were different because we don't have any stereochemistry, right?
It's stereochemistry. In your textbook, does address this. I've never done it. I think it's kind of going a little bit too much than we need to. I think these two H's here are going to be called diastereotopic. And I think, isn't that in the textbook? Diastereotopic. But I'm just sort of not addressing that, so. I think we made enough of the point. Let's move on.
I'll get 5 signals or 6?
No signals.
Let's go with 5, but it's I think it's 6. Okay. I don't want to. We got to cut the line off somewhere, and I don't want to just keep going on and on. But the book does talk about that. Diastereotopic. And you see topic on the end in the textbook. Most books don't get into that, and I've never gotten into it, but this book actually does. I consider it more of an advanced topic. How many signals for this guy? There's 4 H's here. Are any of them the same? A, B, C, D. They're all different. Anybody think they're the same? Guys? Same?
Alright, so you can't just say, like, an example of A and D that they're both next to an electronegative atom. Like, you have to take into account the specific electronegativities of them, which make them different.
Yes, chlorine's more electronegative than bromine. So chlorine is going to de-shield this area more than bromine will de-shield that area. How many signals in the middle here? Those are the same, yeah? Got symmetry here. So what do we got? 2, how many was this? 4? About the one on the end, which is called 1,4-dichlorobenzene. You can buy this at Walmart. They call it mothballs, I think. How many signals? One. Every H is the same. Draw them in. Look at it. Lots of symmetry there. Eugenol, a little bit bigger molecule. We used to make eugenol. I don't think it's in my lab manual. A long time ago, we did something with it. How many proton signals?
Eight.
Is every H like?
I hear 8. Do I hear anything else?
Oh, 7.
Do I hear a 9? Do I hear a 9? Can I get a 9? Can I get a 9? Somebody give me a 9.
No.
How
I feel like there's.
many?
Eight.
Somebody give me a 9.
I got 9.
9. Thank you for the 9. 9, right? These three are the same due to free rotation. I don't know why I'm doing letters. Then we have to count the letters. B. There's one here, that's C. There's one here, that's D. We're doing H now. There's one there, yeah. E. 2 here, but they're same due to free rotation. Pretty sure they're right. We're going to say they're right. F. We got H's here. Let's draw them in. G. H. What is this one? Is that one the same as H? No. H is cis to the big group over here. This one is trans to the big group over here. It's different. That's I. 1, 2, 3, 4, 5, 6, 7, 8, 9. These two are different, even though they're on the same carbon. There's no free rotation. Phenacetin, we're making that next week, right?
Yeah.
How many proton signals? Somebody say 6? I think you may be right. A, B, C, C prime. These two H's are the same. D, D prime. Those two H's are the same of symmetry. E, F. 1, 2, 3, 4, 5, 6.
Are the two C's the same because the nitrogen's pulling stronger than the oxygen that's farther away, so that's not different?
You got free rotation up here. You could argue you don't have free rotation, but I know they're going to be the same. So that implies there's free rotation. This is a single bond, and that should be able to rotate. Good question. Now, of course, you could say, well, isn't there resonance here? There is resonance, right? Isn't that lone pair here? And then you could say, well, Dr. Stevens, shouldn't resonance or conjugation restrict rotation? And then we could go back and forth for an hour. But I just feel I know that, these are going to be the same. Good question. 6 proton. While we're here, how many carbon signals? We're not going to do carbon NMR until way over in the handout. Let's do it here. How many carbon signals? And it's how many unique carbons in the molecule.
Wouldn't this be under the stipulation that they're all carbon-13?
Oh, what?
Wouldn't this be under the stipulation that they're all carbon-13?
Okay, well, good. Okay. What is abundance, natural abundance of C13?
Not as much as 12.
You had me forgetting one, I think on the first day, within the first 10 minutes, I told you this. 1%. About 1%, okay? The 1% of the carbons in your body are C13. 1% of the carbons in that molecule are going to be C13. That's what we'll actually do carbon NMR on. Now, not every molecule will have this carbon here be C13, but because there are gazillions of molecules in your tube, some of them will be C13 and you'll get a signal for them. In the end, we can get a signal for all the carbons, but it's coming from the C13. How many different carbons? Well, that's a carbon, that's unique. Is that carbon different than that one? Sure. Carbon, no carbon, okay? Well, there's no carbon here. Carbon here, right? What is this? E. What is this? E prime. These two carbons are the same due to symmetry. We're doing carbon here. Well, that was different than that one because this one's closer to N, this one's closer to O. This is F prime. G, that carbon there.
Dr. Stevens,
Uh,
where's E at?
Not his alphabet.
He's gonna count them anyways.
did I skip D? D is in David? Yeah, I've always had trouble with it. All right. I'll call this one D. Now we got A, B, C, D, E, F, G. Hey. How many different carbons? 1, 2, 3, 4, 5, 6, 7, 8. 6 different types of hydrogen, 8 different types of carbon, meaning those signals. Now if you flip over, we'll see the proton NMR and carbon NMR in a sequence. Top is the proton, up at 0 to 10 or 12 ppm. Here are your 6 signals. 1, 2, 3, 4, 5, 6. Haven't labeled them which is which. You can maybe do that a little bit later. You'll see that the signals are split, singlet, doublet, triplet, etc. We haven't explained why yet. Carbon NMR, you'll notice that the signals are not split. All the signals are singlets. How many did we expect? 8? 1, 2, 3, 4, 5, 6, 7, 8. Carbon NMR, your baseline goes from 0 to about 200. Same terminology applies. This signal here is the most downfield signal. That's the most upfield signal.
So what is the parts per million exactly measured?
I think it's, we pointed out somewhere here. Next we're going to get a T position. So let's take a quick 2-minute break, stretch your legs. So we'll go till 5:15. Let's just sort of, need to stand up or anything. We'll give it about 30 more minutes because we need to make good progress here.
Dr. Stevens, on some of these, the TMS signal is going to be there, and then some of them it's just removed because it's just not calibrated.
Some of these may be computer generated spectra and they didn't put it, you know. So if we ever see one on zero, like on you all just assume that it's the baseline. We don't have to worry about that to be right. Actually, I don't use TMOs because there's other ways to set your baseline. If you want to know, you can come by and ask. You can actually use your solvent peak to set the baseline, like the DMSO peak.
They're both, I mean, the oxygen on this one. There's no alkenes.
You're probably right.
But even like, you have a different answer now. I don't know.
No, I think you're right. I think I was wrong there.
Hey, Dr. Stevens?
Yeah.
Okay, we looked at that last example we were doing, the number of signals.
Look at which one?
The last example on the number of signals section.
Yeah, we skipped that one. How many proton? Let's go back to that real quick. How many proton signals did you come up with? 4. We got symmetry here, A, B, C, D. That's A prime, B prime, C prime, D prime. Same, 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 same. Thanks. Michael?
When you have symmetry in molecule, so, like, the one right before that, benzene, why does the cube with the nitrogen and the oxygen, why does that still count as symmetry then?
I rationalize it because you got free rotation up there,
Okay.
and it becomes equivalent by free rotation. Now, extra information. You can do NMR like super cold, like at negative 80 degrees, and it will slow down that rotation, and things will become non-equivalent. But we're not going to be doing any of that in this class. Okay. To make them equivalent, a lot of times we're saying that free rotation just sort of, and on the NMR time scale, they become equivalent. Trust me, there's lots of nuances in this stuff. We already give you a literature about it. And you can go on if you're interested in reading more. You can get like books that are just devoted to NMR. We need to get started, guys. Okay, number 2 is going to be peak position. Number of charts. The first chart is sort of the most generic. List sort of functional groups. Again, everything we're doing is proton right now. We can sort of divide this like it's trying to be divided here. Okay, these are divisions that we can focus in on. All right. All right here, what you need to recognize is that this is sp3 CHs. If the H is on an sp3 carbon, it's going to be like in the 1 to 4.5 range, ppm. Now, what's the plainest type of hydrogen where there's no de-shielding? Like this, it's mentioned, there's no halogen or anything. Okay, there's no de-shielding. These are going to be like just plain sp3. This is going to be about 1 ppm, these H's. Now, if you put a bromine here, it's going to start deshielding. And then the H's closest are going to be where?
Farther back.
More downfield because deshielding. But that's right here. This is denoting a CH that's bonded to an electronegative atom like NO or halogen. CH with the carbon, the H can't be bonded to the halogen. C is. That's like this here. The CH with the carbon bonded to a halogen is what? I would say about 3 to 4. Okay? They say 2.5 to 4.5. More downfield. What's in between? CH, where the carbon is bonded to a, most common is carbonyl, where Z is oxygen. Tell me if you can't see. I know it's not the best here. This would be like an example here. This is going to be more downfield from 1. This is going to be like about 2. I would call it about 2 to 3. But it's sort of intermediate. It's not going to be as far downfield as this type of scenario. But what we're talking about is like here. CH with the carbon bonded to a carbonyl, or maybe an alkene. So take some time to see what they're trying to illustrate here with these generic structures. But they're all sp3CHs. But as we get them close to electronegative atoms, they start moving downfield. Okay, come on downfield, you get sp2CHs. 2 different sections though. These are typically your alkene. That's going to be about 5 to 6 ppm. Now your aromatic, that aromatic ring, like a benzene ring, that's even more downfield. That's like 7 to 8. Now we'll routinely say aromatic region is 7 to 8 ppm. Of course, it might be 6 to 9. But 7 to 8, okay? So learn your regions. You might think that the SPCH is even further downfield, but it's actually back upfield with your SP3s. See, I said these are SP3s. But you also have this guy. It's kind of an outlier because it's not as commonly seen. But it's actually back up here. Let's explain that. The explanation introduces an important concept. First off, why is the aromatic CH more downfield than the alkene? If we flip over here, we can see things that look like this. The aromatic has a very large amount of electron density because it's an aromatic system, electron pi system. Lots of electrons leads to more shield, not more, no, hold on, that doesn't make sense. More electrons leads
The
to...
cloud is spread out over a larger area.
Possible. Let's just take it one step at a time. More electrons should lead to more shielding or more deshielding?
More shielding.
More shielding. So aromatics have more electrons, more shielding. Is more shielding moving the peak to the left?
No.
No. More shielding the peak to be to the right. So why is it to the left? That's the answer to everything, right? Well, why resonant? Why the, okay? It's because that field that's opposing, it doesn't always oppose. Well, the magnetic field has field lines. Do you only get field lines with magnetic? But pi system, this is the external magnet. It sets up field lines, the electron circulating here sets up field lines that do this. See the arrows? And it sits here. And out here where the H is this current, is this field opposing this or adding to it? Actually adding to it. It's not opposing. And adding to it is a shielding or de-shielding? It's a de-shielding effect. That's like going out and instead of putting on sunscreen, you put on something that gives you more sun. So this is why the H is actually more downfield, because it's actually out there where it's being de-shielded. This depends on depends on some direction and way the molecule is oriented. Directionality is known as an anisotropic effect. Somewhere it says anisotropic effect on this page. Okay. Now, why is the SPCH to the right, which is shielding or de-shielding? Shielding. Shielding. It's illustrated down here. Okay, first off, here's your triple bond. And it has directionality that leads to this. And this magnetic field circulates like this. Let's draw it larger so we get up in here. And where the H is this opposing or adding to this? You see where that H is, and how this is oriented, it's actually opposing, which is a shielding or de-shielding. It's the shielding effect. That's why this particular H is actually way more to the right. These are called anisotropic effects that have to depend on the orientation of the molecule in the field. Okay. We may refer to that a little bit when we get to aromatic chemistry. There's other tables here. We pretty much said as much as you need. The others are just there for your reference. Okay, we'll look at along the way. And we're precise. Okay, let's look at signal integration. Area under the curve, we've already mentioned this a little bit. Look at this molecule here. How many signals do you expect? A, and B? 2 signals?
Yeah.
How many H's are A? How many are B? 92, that's your ratio. We're going to get that from the integration. Here are your 2 signals. Which one do you expect to be more downfield, A or B? Downfield is de-shielded, that's B. The one closer to the bromine, it acts as a de-shielder. Okay. This is actually B. What do we say when it's like bonded to a bromine? About 3 to 4? You see how this is about 3 to 4? These others are more like plain alkane, so they're going to be closer to 1. This is an integral curve or line. This is something that you get from the instrument, and you use it by, you measure from where it starts rising to where it ends. And you measure this length. See, integrating over the curve, the area under the curve here, there. And that length should correlate with 9 to 2. Now, if you didn't know it was 9 to 2, and you didn't know structure, how would you figure out it was 9 to 2? So you can measure it. This length is inches. This here is it's like 15 inches. Measure this right? I don't think I measured it. I think it's more like boom, boom. Integration is a little bit tricky. It's not going to be actually precise. The only reason I know I need to be measured is really because I already know the answer. I'm going to adjust this to like 2.5. Okay? 2.5 to 15. That's your relative ratio. Let's turn this into 1 by dividing by 2.5 equals 1. Divide that by 2.5, what do we get? 6?
7.
Yeah, 6, right? So it's a 1 to 6 ratio. What is this ratio? It's not 1 to 6, it's 1 to 4.5. I don't know if we measured this yesterday or what. Now they give you a measurement. I don't know what that 1.6 refers to. It's not inches.
Look at how many blocks, grid blocks.
Might be grid blocks. I tried to lower that to match it, and then I think I overcompensated. I think this may be more like 3. 3 divided by 3 is 1. 15 divided by 3 is 5. That gives us a 1 to 5. Getting to say it's closer. Okay. Basically, you measure this. There'll be some in the workbook. These distances equal. The ratio of your differences is equivalent to the ratio of the number of pages in the volume. Okay, here's the thing about integral curves. I don't use them on the practice problems I give you. I actually tell you the integration. Okay? Go back. You don't turn here. Look at the very beginning. I told you this was a triplet for 2 h's. I'm telling you it's 2 h's. Okay? But here's the thing. On standardized exams, such as the exam in this course, or maybe a DCAT or an MCAT, they may throw you some integral lines that you have to work with. Okay? Let's look at the one down here. I mean, this is an integration. It's some arbitrary number. We got to boil it down to a ratio. We can do that by dividing this by 23. Get 1. Divide that by 23. What do you get? Approximately. That's like 1.5, right? Well, guess what? You can't have 1.5 hydrogens. What if we divide this by 23? What do you get? Roughly what? Integration is never exact. I'm going to say 2. Do you think we have 1 hydrogen, 1.5, and 2? What do you think instead we have?
4, 3, and 2.
Let's change this to 2, this to what? 3, and this to 4. You can't have a half hydrogen. Looks like the integration is telling us it's 2, 3, and 4 in terms of number of H's. Now, I know this compound, and that should actually be 5. See, that's because we rounded it to 2. That was a low rounding. It's more like 2. It's more like 2.5 almost. And if we call it 2.5, we would have listed 5 when we doubled it. Okay. So there's some information there. But look at this. Even if you didn't know peak placement, since this is a lower integrating signal, that tells you that it's this guy, right? because that signal is going to be higher integrated. Okay. So maybe coming around the home stretch for today. Let's do this here. Here's an NMR of this compound. How many signals? Based on lettering, 5. If I agree the two methyls on the end are the same, we both bind into a CH. 5 signals. Here are your 5. 1, 2, 3, 4, 5. What is this? That's where they're blowing up this signal so you can see it better. What is this? Look at that baseline. 1.1, 2. That's where they're blowing up that signal there at 1.1 so you can see it. The reason is you can see it's a doublet. Where here it almost looks like it's just a singlet. So you can see the multiplicity better. Okay, in terms of your integration, well, based on structure, how many A hydrogens are there? 3, so you expect to integrate for 3. How many B?
6.
B's over there, 6. How many C? D? And E? Just 1. So that's your integration. Before we do multiplicity, let's see if we can assign some signals based on peak position. Which signal would you expect to be most downfield? Most de-shielded. Which one is that? Nearest the oxygen? Yes. Yes. Thinking this is E. Most downfield due to that oxygen. Which signal would be most upfield? That is, it's going to be the one furthest away from a de-shielding effect. A. And indeed, this is A over here. A is getting to be more just like plain alkane. All right, and let's do multiplicity. A is first. Is this signal a singlet, triplet, doublet? Singlet, doublet, triplet? It's got 3 lines. Can you see them? 1, 2, 3. A is a triplet. I'll write a T like that, curved at the bottom, so it doesn't look like a plus sign. Let's get to E. What do you want to call E? Things are going to be singlets, doublets, triplets, quartets. If it's more than 4, we're going to call it a multiple. How many lines here? 7. You can call it a septet. We're just going to call it a multiplet. Okay? Multiple. Okay, I see now. I really wanted to do integration first because we don't know which signals these are. Let's halt that. Let's assign signals based on integration. Let's use our integral curve. Okay, we measure from here to here. Instead of using the ruler, I want to use my finger gap. So that is that long. So that's that long. How many H's is this? 1, or we could get to that. So if that's 1, how many is this? 2. It looks like it's twice as long as that. I want to say that's 1H. I'm going to say this is 2H. If that's 2H, how many is that? It looks the same. I'm going to say that's 2H. If that's 2H, how many is this?
6.
Knowing structure, we can take a good guess that it's what? Looks like it's 3 of those, so it's 6. So if that's 2H, how many is this last one? It looks like it's not double for 4, but it's what? Looks like it's 1.5 of my finger gaps. So what's 1.5 of 2? 2 times 1.5. 3H. That's, I could have did it with a ruler, instead I used my finger gap. Okay? Because it's pretty big here. Alright, you got that written down, and we'll put it back up. Now what we just wrote there should be here, right? Well, not necessarily, because we got to have letters. Let's get some letters up here and keep it. So which is this, H or E? That's E, which is 1H, right? Didn't we say that's 1H? Let's skip these two. What's this one on the end? A, which is how many H's? 3. Isn't that what we got with our fingers? This guy here is 6, so it's what? B, because there's 6 of those. We got 2 and 2, which is what? C and D. Which is which, though? Integration doesn't tell us, because they're both 2.
D would be further down.
Tell me something.
C is upfield.
Which one's upfield?
C.
C is more upfield,
D is more down.
or you can say D is more downfield, because it's closer to that carbonyl. I would call this D and this C. As you get away from that carbonyl, DCA. Multiplicity, we called A was a, what, triplet? E was a multiplet. What is B? It's expanded so you can see it. It's 2 lines. Doublet. C is this one. Yeah, they didn't expand it, did they? As you can tell, it's multiplet. C is a multiplet. D, what is D? Yeah, it is a triplet. That's the so-called multiplicity of each signal.
How does that relate to the structure of the molecule multiplicity?
That's the next topic. Okay. This is going to be the last page, and this is where we ended yesterday with this page. Let's get through this page here, guys. This gets at the question that was just asked. Why are they doublets and triplets? Okay. It's called signal splitting, also coupling. Let's just get right to it. Look at this compound. This signal here will be a doublet. This methyl will give you a doublet. Why? It turns out that the neighbor is a nucleus, hydrogen nucleus. And the hydrogen, the neighboring hydrogen, that nucleus has a magnetic moment with direction, and that moment can be in line with the external field, or it can oppose it. Now this is the signal we're observing. Some of the molecules, the neighbor acts as a de-shielder. But in some of the molecules, the neighbor acts not as a de-shielder, as a shielder. I'm sorry, did I get that one right? Let's start over. This scenario is opposing it, so this H is acting as a shielder. But in this scenario, the neighbor is acting as a de-shielder. You have two different situations. In the end, it's like two signals. Some of the methyls give a signal based on the neighbor being in this form. Some of the methyls give a signal with the neighbor based on that. We don't call it two signals. We call it a doublet. Okay? Now, let's look down here. What about this guy? This CH3 will be a triplet. Why? It has nothing to do with that. It has to do with the neighbors. In this case, we have two neighbors. Now, I didn't show all the structures out. Instead, I just did, I could have just did up and down for those. Here, these two. These two neighbors could both be in line with the magnetic field, or they both could oppose it. One could be in line, one could be opposed, or the other one could be in line and the other one can oppose. If the H's are the same, these scenarios are the same. It's just twice as likely to have this scenario. So basically, you have some molecules that are experiencing this neighbor effect, some molecules that are experiencing this neighbor effect, and some molecules that are experiencing this. You actually get three signals, but we don't call it three signals. We call it a triplet. Important, the triplet has line length short, tall, short, which equilibrates or equals the center possibility is twice as likely, and so that signal is going to be stronger than the two on the side. So it's really three signals, but we don't call it three signals. We call it a triplet signal. Seems like every time you turn around, there's another magnetic field that's doing something. Now we got the neighboring field doing something. Okay? How about this guy? This is the same structure up above, except now let's look at this H. This H has three neighbors. We'll clarify what neighbors mean. Now here, all three of these neighbors can be in line, all three can be opposing. Or you can have two in line, one opposing, but you have three ways to have that. These two can be in line, these two can be in line, or those two can be in line. If the H's are the same, which they are, all three of these scenarios are the same. Then you can have a scenario where one is in line but two oppose. Or maybe that one's in line and these two oppose. Or this one's in line and those two oppose. Those are all the same. But it is 3 times as likely to have this scenario. How many different scenarios are here? 4 scenarios, so you get 4 signals. We don't call it 4 signals, we call it a quartet. What's the intensity going to look like? 1, 3, 3, 1. 1, this B actually should be higher. 1, 3, 3, 1. The quartet looks like this. Not like that. The 2 middle are 3 times as likely. Now, every time do you have to go through all this to figure out what it's going to be? No. This can be summed up with a rule, the n+1 rule. This will tell you your splitting expected, where n is the number of equivalent NMR active neighbors with a spin I1/2. At this point, it's the number of neighbors. How far away? 2 or 3 sigma bonds away. No more than 3 sigma bonds away. Further possible, but basic coupling is 3 sigma bonds away. For example, how many neighboring hydrogens are within 3 sigma bonds of these H's? Let's draw the H's. They're all the same. This one. How many neighbor H's within 3 sigma bonds? First off, that is a neighbor, but it's the same H. Same H's don't split each other. 1, 2, 3. There's 3 bonds between this and this. See, that's a neighbor in this definition. How many are there? 1. So N is 1. So we got 1 plus 1 equals what? 2. Very good. 2. So what do we expect for this? Double it. And that's what I told you right here, right? See it at the top? Double it. Let's do this one. Here, how many neighbors within 3 sigma bonds of this H? We're looking at this signal. How many neighbors are within 3 sigma bonds? Neighboring H's? 3. Each one of these is within 3 sigma bonds of that guy. So N plus 1. How many neighbors? 3. 3 plus 1 equals? Good. So what do we expect for this guy? Quartet. Isn't that what I told you? Where does it say quartet?
You said it out loud.
We said it out loud.
No, it's not written.
You asked us on the paper.
Okay. You wrote quartet? Okay, there you go. Sort of to close this up here, let's go back, let's go to the previous slide here, this guy over here. Don't look at what we wrote, just look at structure. A. Don't look at what you wrote, don't cheat. Do you expect A to be singlet, doublet, triplet, quartet, what? How many neighbors within 3 sigma bonds?
2.
Yeah. Are these within 3 sigma bonds?
No.
No. 2. 2 plus 1 is 3. Triplet. Is that what we wrote? Yes. How about for D? How many neighbors within 3 sigma bonds? 2. N plus 1 is 3. Triplet. D should be triplet. Is that what we got? B. How many H's within 3 sigma bonds? 1. So N plus 1 is 2. What do we have for B? Doublet? Okay. E. How many H's within 3 sigma bonds? 6. Both methyls are within 3 sigma bonds, total of 6. Are the 2 methyls the same? Because they have to be equivalent, ion or non-equivalent. Are all those 6 the same? Yes. So we can do 6 plus 1. And we expect what for E? 7 lines, septet. We call it a multiplet. But if you want to count your lines, there they are. How many do you see? 1, 2, 3, 4, 5, 6, 7. There are your 7 lines. C. How many neighbors within 5? You got 3 on the one side, 2 on the 5. What do you expect? 6. N plus 1 is 6. You would be wrong. Why are we wrong in this case? What did I underline in the rule? N plus 1 rule. No, I underlined another word. It'd be equivalent to do this. Are these neighbors and those neighbors the same? Doesn't work. This is complex splitting. It's actually another page, but we can do it right here real quick, and this is where I think we'll end. We have to do the N plus 1 rule for each type of neighbor. The neighbors over here split the C signal into what? There's 3 neighbors over here. N plus 1 is 4. Quartet. And so the C signal, we're talking about the C signal, A splits the C signal into a quartet. Now let's do the n+1 rule again for the D neighbors. How many D neighbors? 2. n+1 is 3. Triplet. The D splits each of these lines into a triplet. This becomes a triplet, this becomes a triplet, this becomes a triplet, this becomes a triplet. I'm not going to worry about the intensity of each. Just looking at the total number. How many lines do you get? 12 lines. It's not 6, it's 12. Don't think it's always multiplied by 2. It's called complex splitting. All it means is you have to do the n+1 rule twice. That's actually all shown on one of the next pages, but I just gave you the overview. Okay? In the end, what do you want to call such a signal? Singlet? Double? In the end, it's still going to be a multiplet. Where is it at? That little guy right there? You see, it splits so much, you can't even hardly tell. It's a multiplet still. But theoretically, you should expect a couple lines. Okay. The warm-up page again, like I told you this morning. Start doing some practice. Hopefully you'll find those in the warm-up. Pretty straightforward now. There's also problems in the workbook. All right, we're only 5 minutes late. There's lots to do tomorrow. Again, I don't think it's that difficult, it's just a big bit. Y'all have a good evening and be safe. And Wednesday morning? Okay, guys.